Hi everyone, welcome back. This is Spectre P, and we are Spectre AI. When people talk about quantum computing, they often talk as if there's a single machine waiting to be built, a single path that just needs more time, funding, or clever algorithms. In reality, what we call quantum computing is a family of very different physical architectures, each built on a different way of storing, controlling, and measuring quantum information. Those physical choices matter far more than marketing labels, qubit counts, or roadmap promises, because they determine what kind of errors dominate, how systems scale, what kind of environments they require, and ultimately, what kinds of problems they can realistically solve. In this video, we're going to compare the major quantum hardware architectures side by side, not as vendors or platforms, but as physical systems. On the far left are superconducting qubits, which rely on cryogenic circuits operating near absolute zero, offering fast gate speeds at the cost of extreme cooling and wiring complexity. Next are trapped ions, where individual atoms are suspended in electromagnetic fields and controlled with lasers, trading slower operations for long coherence and high precision. At the center are neutral atom systems, which use optical lattices or tweezers to arrange large arrays of atoms, promising impressive scaling density while introducing new control and uniformity challenges. To the right are photonic approaches, which operate largely at room temperature and encode quantum information in light itself, shifting the burden from cryogenics to fabrication, optics, and measurement. And on the far right are topological and Majorana-based approaches, which aim to encode quantum information in exotic states of matter that are theoretically protected from noise, but remain experimentally uncertain. The point of this comparison is not to declare a winner. It's to apply a common framework to all of them and ask the same questions of each. What does universality mean in practice? Where do errors actually come from? What limits scale first? And which challenges are engineering problems versus unsolved physics? By grounding the discussion in hardware reality rather than abstract models, we can see why different architectures excel at different tasks, why timelines vary so widely, and why no single approach dominates across all dimensions. This is a comparison of trade-offs, not slogans, and understanding those trade-offs is essential if we want to talk honestly about the future of quantum computing. Before we compare any specific quantum hardware, we need a common framework. Otherwise, the discussion collapses into marketing claims, cherry-picked benchmarks, or arguments where each platform is judged by its own preferred criteria. The table you're looking at is that framework. Each row represents a fundamentally different quantum hardware architecture, and each column represents a constraint that matters in real machines, not just in theory. Universality asks whether a system can realistically support general-purpose quantum computation, not just special case demonstrations. Error sources force us to identify what actually limits performance in practice: decoherence, control noise, measurement error, crosstalk, or something else entirely. Scalability examines what breaks first as systems grow: wiring, lasers, fabrication yield, calibration overhead, or fundamental physical limits. Operating environment captures the non-negotiable realities of temperature, vacuum, optics, and control infrastructure that shape deployment. And finally, engineering versus physics risk separates problems that can plausibly be solved with time, money, and better engineering from problems that require new physics or unproven assumptions. The red question marks are intentional. At this point, nothing has been scored, ranked, or declared superior. Every architecture starts with the same unknowns, and over the rest of this video we'll fill in this table methodically, using the same criteria for every platform. The goal is not to crown a winner, but to understand the trade-offs each approach makes, what those trade-offs imply for real systems, and why different architectures excel, or fail, in different ways. Let's now discuss in detail the chart you just saw. First, we'll go across the columns of the chart, then its rows. When people say a quantum computer is universal, they usually mean something very specific in theory, that any quantum operation can be approximated arbitrarily while using a small, fixed set of gates, like the Hadamard, T, and C0 gates shown here. In an abstract model, that definition is clean and mathematically sound. But real quantum hardware does not implement these ideal gates directly. Every physical system has its own native operations, rotations, swaps, conditional interactions that arise naturally from the underlying physics. Bridging the gap between what theory wants and what hardware provides requires compilation. Logical circuits expressed in an ideal universal gate set must be translated into long sequences of hardware-native gates that the machine can actually execute. This translation is not free. Each additional gate adds time, control complexity, and error, and the cost of that translation depends heavily on the architecture. Two systems can both be universal in theory, while having radically different practical universality in practice, simply because one pays a much higher compilation penalty than the other. That distinction between theoretical universality and usable universality is what matters when we compare hardware platforms honestly. In the next step, we'll make that idea precise by looking at how universality is quantified, how approximation overhead scales, and why some architectures pay a much steeper price than others as circuits grow. Up to this point, we've been talking about universality conceptually. Now we're going to make that idea precise using the actual mathematical definition and then connect it directly to hardware reality. In quantum computing, a machine is called universal if it can approximate any unitary operation acting on n qubits. Formally, that means any unitary U that lives in the special unitary group SU of 2 to the n. That's SU open parenthesis, 2 raised to the n close parenthesis. The definition says that for any desired accuracy, and here accuracy is written as epsilon, that's the Greek letter epsilon, greater than 0, there exists a quantum circuit built from a finite gate, set G, such that the distance between the ideal operation U and the implemented circuit C of G is less than or equal to epsilon. In plain language, if you're willing to tolerate a small error epsilon, you can approximate any quantum operation using only a fixed, finite set of gates. The next question is where the cost shows up. That cost appears in circuit depth, meaning how many sequential gate operations you need to apply. A key result, often associated with the Solovay-Kitaev theorem, tells us how that depth scales as we demand higher accuracy. Specifically, the circuit depth required to reach accuracy epsilon grows on the order of log to the power c of 1 over epsilon. That's written as big O of log raised to the CO of 1 divided by epsilon. Here, Ca is a constant, typically around 3 to 4. What matters is not the exact value of C, but the fact that this scaling is asymptotic. As epsilon gets smaller, meaning as we demand more accuracy, the circuit gets longer, sometimes much longer. And crucially, the constants hidden in that big O notation depend on the hardware's native gate set. That's where the concrete example on the right comes in. Suppose the target operation is a single qubit rotation around the z-axis by an angle theta. That's rz of theta. In an architecture where rz is a native gate, that operation can be implemented directly using one physical gate. In a different architecture that does not have native z rotations, the same operation must be compiled out of a universal gate set like H and T. That's Hadamard and T gates, resulting in a long sequence of gates, H, T dagger, H, and so on. Mathematically, both architectures are universal. They can both approximate the same unitary operation to arbitrary accuracy. but practically they are very different. One uses a single gate. The other uses many gates, accumulating more error, taking more time, and consuming more control resources. The key takeaway from this example is that universality is not a binary property. It's not just yes or no. Two architectures can both be universal in theory while having radically different practical universality, once compilation depth, error accumulation, and runtime are taken into account. That difference is what we'll use this framework to expose as we move through the hardware architectures one by one. When people talk about error in quantum computers, it's often described as if there's a single noise knob you can just turn down. In reality, error comes from multiple distinct physical mechanisms, and each architecture is dominated by a different combination of them. The first is decoherence. This is the loss of quantum information due to interaction with the environment. Qubits are never perfectly isolated, and over time their quantum state drifts or decays as energy, heat, or electromagnetic noise leaks in. Decoherence sets a fundamental time limit on how long information can be stored without active correction. Next is control noise. Even if a qubit itself is stable, the signals used to manipulate it, microwave pulses, laser beams, voltages, are imperfect. Small timing errors, amplitude fluctuations, or phase noise in the control system translate directly into gate errors. These are not quantum mysteries. They are classical engineering imperfections that show up every time we try to steer a fragile quantum system precisely. Crosstalk is a related but distinct problem. When you operate on one qubit, nearby qubits can be unintentionally affected through stray fields, shared control lines, or overlapping laser profiles. As systems scale, crosstalk often increases faster than expected, making isolation between qubits harder rather than easier. Measurement error appears when we try to read out the state of a qubit. Detectors are imperfect, signals overlap, and readout thresholds are noisy, so the measured result does not always match the actual quantum state. Even if everything before measurement were ideal, errors can still be introduced at the final step. Leakage is another critical source. Many physical qubits are not true two-level systems. They have extra energy levels. During gate operations, population can leak out of the computational subspace into these unwanted states, where it no longer behaves like a logical qubit at all. Leakage errors are especially dangerous because they are not easily corrected by standard error correction codes. Finally, all of these error sources interact. Decoherence limits how long gates can run, control noise accumulates with circuit depth, crosstalk worsens with density, measurement error affects feedback and correction, and leakage can silently corrupt the computation. The key point of this slide is that error is not a single quantity, it is a profile. And understanding which of these mechanisms dominates is essential for judging how any given quantum hardware architecture will behave as it scales. When people talk about scaling quantum computers, they often focus on qubit count as if adding more qubits were the main challenge. In practice, qubits are rarely the first thing that breaks. What limits scale is the infrastructure wrapped around them. As the number of qubits increases, the number of control lines grows, often faster than linearly, bringing with it routing complexity, cross-coupling, and signal integrity problems. In architectures that rely on optical control, scaling also means more lasers, more beam paths, tighter alignment tolerances, and greater sensitivity to drift. None of these challenges are abstract. They are physical constraints that show up immediately as systems grow. On top of that sits calibration overhead. Every additional qubit adds new parameters that must be tuned, stabilized, and re-verified continuously. As systems scale, calibration time can grow to the point where the machine spends more time being maintained than computing. The key point is that scalability is not just about whether qubits can exist in larger numbers. It's about whether the supporting control, measurement, and calibration infrastructure can grow at the same pace without overwhelming the system. Different hardware architectures hit these scaling walls in different ways, but all of them encounter a point where adding qubits becomes harder not because of quantum theory, but because of engineering complexity. Understanding where that wall appears and what causes it is essential when comparing architectures honestly. Every quantum hardware architecture lives or dies by the physical environment it requires. On the left, superconducting qubits operate inside dilution refrigerators at temperatures measured in millikelvin. At these temperatures, thermal noise is suppressed enough to preserve fragile quantum states, but the cost is extreme cooling infrastructure, limited physical access, and severe constraints on wiring, control density, and heat dissipation. In the center, trapped ions and neutral atoms require ultra-high vacuum chambers combined with precisely aligned laser systems. The environment must be clean, stable, and vibration-free, with optical access maintained at all times. While these systems avoid cryogenics, they replace it with complexity in optics, alignment, and environmental stability. On the right, photonic quantum hardware operates largely at or near room temperature, embedding quantum behavior directly into optical circuits and waveguides. This removes the need for extreme cooling or vacuum, but shifts the challenge to fabrication precision, photon generation, loss management, and high-efficiency detectors. The key point is that operating environment is not an implementation detail. It is a defining architectural constraint. Temperature, vacuum, optics, and control requirements dictate how systems scale, how they are maintained, and what kinds of engineering trade-offs are unavoidable. When we compare quantum architectures, we are not just comparing qubits. We are comparing entire physical ecosystems that must remain stable for computation to work at all. At this point, we need to separate two very different kinds of risk that are often mixed together in quantum discussions: engineering risk and physics risk. Engineering risk refers to problems we already know how to approach in principle. These include calibration complexity, manufacturing scale-up, wiring density, crosstalk, laser and optic stability, and the development of reliable room temperature detectors. None of these are easy, but they are familiar categories of problems. They improve with time, money, iteration, better tooling, and accumulated experience. Historically, engineering risk is where progress looks slow at first and then accelerates as systems mature. Physics risk is different. Physics risk comes from limits or unknowns in the underlying behavior of the system itself. Thermal fluctuations, ion heating, photon loss, finite decoherence times, leakage out of the computational subspace, and in some cases, decoherence mechanisms that are not yet fully understood all fall into this category. These are not problems you can simply brute force with more resources. Some of them represent hard limits, and others represent unknowns where it's not yet clear whether a clean solution exists at all. The reason this distinction matters is that different quantum hardware architectures sit in very different places on this spectrum. Some approaches face mostly engineering risk, which suggests a long but relatively predictable development path. Others carry significant physics risk, meaning their ultimate scalability depends on breakthroughs that may or may not arrive. When we compare architectures honestly, we're not just asking which one works today, but which challenges are fundamentally solvable and which ones remain open questions. That lens will be critical as we now move from abstract criteria to evaluating each hardware platform in turn. Superconducting qubits are built from lithographically fabricated circuits that behave quantum mechanically only when cooled to extremely low temperatures, typically on the order of 10 to 20 millikelvin, which is why these systems live inside dilution refrigerators like the one shown here, with multiple temperature stages stacked vertically above the qubit chip, each stage responsible for intercepting heat and noise, before it can reach the coldest plate where computation happens. At these temperatures, superconducting materials exhibit low loss and allow microwave resonators and Josephson junctions to act as controllable two-level quantum systems, enabling very fast gate operations measured in tens of nanoseconds, which is one of the major strengths of this architecture. But that speed comes at the cost of a dense control stack because every qubit requires multiple microwave drive lines, readout lines, filters, attenuators, and amplifiers that must pass through each temperature stage without introducing excess thermal load or electromagnetic noise. As qubit counts increase, wiring density grows rapidly, leading to routing congestion, crosstalk, and limits on how many control lines can physically fit through the refrigerator while maintaining thermal isolation. And this wiring problem is often the first scalability wall encountered rather than qubit fabrication itself. Error sources in superconducting systems are dominated by decoherence from material defects, dielectric loss, and electromagnetic noise, as well as control noise from imperfect microwave pulses and calibration drift, which means performance depends heavily on fabrication quality and continuous recalibration. Universality is achieved through native single-qubit rotations and two-qubit entangling gates, but compiled circuits can grow deep quickly, amplifying control and decoherence errors, especially as systems scale. From a risk perspective, most challenges faced by superconducting qubits fall into the engineering category rather than unknown physics, meaning progress is plausible through better materials, improved fabrication, cryogenic integration, and control electronics. But the operating environment itself is unforgiving, expensive, and physically complex. And that environment fundamentally shapes how far this architecture can scale before wiring, cooling power, and calibration overhead dominate the system. Superconducting qubits therefore represent a fast, flexible, and experimentally mature approach to quantum computing, but one whose long-term scalability is tightly constrained by cryogenics and control infrastructure rather than abstract quantum principles. Trapped ion quantum computers take a fundamentally different approach by using individual atoms as qubits, suspended in space inside an ultra-high vacuum chamber, and confined by carefully shaped electromagnetic fields, which means the qubits themselves are nearly identical by nature rather than fabricated objects, giving this architecture exceptionally long coherence times and very high intrinsic qubit quality. Quantum operations are performed by addressing the ions with precisely tuned laser beams that drive internal electronic transitions or collective vibrational modes, allowing entangling gates that are extremely accurate but significantly slower than those used in superconducting systems, often operating on microsecond timescales rather than nanoseconds. This speed difference is not a minor detail because slower gates mean that even with long coherence, total circuit depth becomes a limiting factor for practical algorithms. Control complexity in trapped ion systems shifts away from wiring and toward optics, as each qubit must be individually illuminated and measured with stable, well-aligned laser beams, and as systems scale, the number of lasers, beam paths, modulators, and optical components grows quickly, increasing sensitivity to drift, misalignment, and calibration overhead. Scalability challenges here are dominated not by cryogenics, but by the difficulty of maintaining precise optical control over large ion chains or arrays without introducing crosstalk or mode crowding, which can degrade gate fidelity as more qubits are added. Universality is achieved naturally through native single-qubit rotations and multi-qubit entangling gates mediated by shared motional modes. But compilation overhead can still grow as algorithms become more complex, especially when routing interactions across distant ions. From a risk perspective, trapped ion systems sit in an interesting middle ground because many of their challenges are engineering-driven, such as laser stability, vacuum quality, and optical scaling, while others touch deeper physics limits related to ion heating and collective mode control as system size increases. Overall, trapped ions represent one of the cleanest and most precise quantum hardware platforms available today, offering excellent fidelity and coherence at the cost of speed and optical complexity, making them particularly strong for smaller, high-quality systems while raising open questions about how far they can scale before control and calibration dominate performance. Neutral atom quantum computing takes yet another distinct approach by using individual atoms as qubits, arranged in large, highly regular arrays using tightly focused laser beams known as optical tweezers, which trap and hold each atom in place without requiring cryogenic temperatures or physical wiring to each qubit. Because neutral atoms are identical by nature and interact weakly with their environment, this architecture offers excellent uniformity and the ability to scale to very large qubit counts within a single module, sometimes reaching hundreds or even thousands of atoms arranged in two-dimensional or three-dimensional lattices. Quantum operations are performed by illuminating selected atoms or regions of the array with additional laser fields that induce controlled interactions, often through excited Rydberg states, enabling entanglement across many qubits simultaneously and allowing a high degree of parallelism in operations. This parallelism is one of the major strengths of neutral atom systems because it allows many gates to be applied at once rather than sequentially, which can partially offset slower gate speeds compared to superconducting platforms. However, this density and parallelism come with trade-offs because individual qubit control is generally weaker and less precise than in trapped ion systems, making it harder to address single qubits without affecting nearby atoms, especially as arrays become more crowded. Crosstalk between neighboring sites, laser beam overlap, and variations in trap depth and alignment can all introduce errors that grow as the system scales. Universality is achieved through combinations of global and local laser-driven operations, but compilation strategies must carefully balance parallel execution against control precision to avoid accumulating correlated errors. From an operating environment perspective, neutral atom systems avoid cryogenics and ultra-high vacuum complexity seen in other architectures, but they demand extremely stable, high-power laser systems and precise optical control over large areas, which becomes increasingly challenging as arrays expand. In terms of risk, many of the obstacles facing neutral atom quantum computing fall into the engineering category, such as improving laser stability, addressing fidelity, and control electronics, while some physics risks remain around interaction strength, decoherence in excited states, and error correlations at scale. Overall, neutral atom architectures are attractive for their impressive qubit density and parallelism, but their long-term performance hinges on whether precise control and error management can keep pace as systems grow larger and more complex. Photonic quantum computing takes a fundamentally different path by encoding quantum information directly into photons and manipulating that information using integrated optical circuits fabricated on a chip, which is why the system you're looking at resembles a dense network of waveguides, beam splitters, phase shifters, and detectors, rather than a refrigerator or a vacuum chamber. Photons are attractive as qubits because they interact weakly with the environment, allowing operation at or near room temperature and enabling massive parallelism since many optical modes can propagate simultaneously without direct interference. And this makes photonic architectures conceptually appealing for large-scale systems. Computation is performed through interference and measurement, with quantum gates implemented by carefully engineered optical paths and phase shifts, often relying on measurement-based or linear optical quantum computing models rather than direct two-qubit interactions. However, the dominant constraint in photonic systems is loss, because every optical component, every waveguide, bend, beam splitter, phase shifter, and detector introduces some probability that a photon is absorbed, scattered, or lost entirely, And unlike decoherence in matter-based qubits, lost photons cannot be recovered or corrected by standard error correction codes. As circuits grow deeper and larger, losses compound exponentially, which means scalability is governed less by control complexity and more by fabrication quality, optical efficiency, and detector performance. Universality is achieved through large interferometric networks and adaptive measurements, but the practical cost of compiling algorithms into these networks can be extremely high, requiring many optical elements and precise calibration to maintain interference visibility. From an operating environment perspective, photonic systems avoid cryogenics and ultra-high vacuum, which shifts much of the risk away from cooling and isolation and toward nanofabrication yield, on-chip integration, and system-level loss budgeting. In terms of risk, photonic quantum computing is dominated by engineering challenges rather than unknown physics, but those engineering challenges are unforgiving because even small improvements in loss per component are required to unlock large increases in circuit depth. Overall, photonic architectures offer a compelling vision of room temperature, highly parallel quantum computation, but their success hinges on whether optical loss can be driven low enough, consistently enough, to support deep, fault-tolerant quantum circuits at scale. Topological quantum computing is built around the idea that quantum information can be stored non-locally in special quantum states that are inherently protected from many common error mechanisms. And the most well-known proposal in this category uses what are called Majorana modes, which are exotic quasi-particles that can emerge at the ends of carefully engineered superconducting nanowires under very specific conditions. The core promise of Majorana-based qubits is fault tolerance by design, meaning that the logical qubit is encoded across spatially separated modes rather than localized physical degrees of freedom, so small local disturbances cannot easily corrupt the stored information. Quantum operations in this framework are performed by physically exchanging, or braiding, these Majorana modes along controlled paths, and the outcome of the computation depends only on the topology of the braiding process, not the precise timing or details of the motion, which is why this approach is theoretically attractive as a route to intrinsically robust quantum computation. If fully realized, topological qubits could dramatically reduce the overhead required for error correction, because many error channels would be suppressed at the hardware level rather than corrected in software. However, this elegance comes with substantial unresolved physics risk, because unambiguous experimental evidence of stable, controllable Majorana modes suitable for quantum computation remains limited, and many experimental signatures can be mimicked by more conventional effects. Building and operating these systems requires extreme material purity, precise electrostatic control, superconductivity, and often cryogenic environments, all while maintaining conditions where the desired topological phase actually exists. Universality in topological systems is also non-trivial, because while braiding operations provide a set of protected gates, additional unprotected operations are typically required to achieve full universality, reintroducing conventional error channels. As a result, topological quantum computing sits at the far end of the spectrum in terms of physics risk, offering the potential for revolutionary fault tolerance if the underlying assumptions hold, but carrying significant uncertainty about feasibility, timelines, and scalability. Majorana-based approaches therefore represent one of the most conceptually compelling visions for quantum computing, but also one of the least experimentally mature, making them a high-risk, high-reward architecture that depends critically on breakthroughs in both materials, science, and fundamental condensed matter physics. Here we finally apply the same ruler to every architecture using the framework we defined earlier, and it's important to be clear about how to read it. Each row corresponds to one of the core constraints we care about, and each column corresponds to a specific hardware architecture. The numbers you see are on a qualitative scale from 0 to 10, where 0 means fundamentally poor performance relative to the others, 10 means comparatively strong performance, and values in between represent trade-offs rather than absolute judgments. These numbers are not meant to be added, averaged, or combined into a single score. Each axis stands on its own because universality, scalability, operating environment, and risk are not interchangeable dimensions. A strong score in one category does not cancel out a weakness in another. For example, superconducting systems score relatively high in universality and maturity, reflecting fast gates and experimental progress, but score lower in operating environment because of the extreme cryogenic requirements. Trapped ion systems score well in universality and coherence, but show constraints in scalability due to optical control complexity. Neutral atom systems score high in qubit density and parallelism, but face challenges in individual control and error management as arrays grow. Photonic systems stand out in operating environment and parallelism, but suffer from loss that compounds rapidly with circuit depth. Topological approaches score very high on theoretical fault tolerance, but also carry the highest physics risk due to unresolved experimental questions. The purpose of this table is not to declare a winner, but to make the trade-offs explicit. Every architecture makes different compromises, and those compromises determine what kinds of problems each system is likely to be good at, how far it can realistically scale, and what risks dominate its development path. This ruler lets us compare architectures honestly, without collapsing a multidimensional reality into a single misleading number. Now we come to our most important question. Which architecture is best for quantum security? Here we see a clear line between quantum hardware architectures and what they are actually best suited for from a security perspective, because quantum security and quantum computation are often discussed as if they are the same problem when, in practice, they are not. Photonic systems stand out as the strongest fit for real-world quantum security deployment, including quantum key distribution, quantum random number generation, and secure optical communications, because they operate directly on photons, which are the native carriers of quantum information in communication networks, and because their risks are dominated by engineering challenges like loss, detectors, and integration rather than unresolved physics. These systems can be deployed today, scaled incrementally, and integrated into existing fiber and free space infrastructure. Superconducting systems, while powerful and experimentally mature for computation, are generally not a natural fit for quantum security deployment because they require extreme cryogenic environments and are optimized for fast gate operations rather than long-distance quantum communication, even though they play an important role in developing large-scale universal quantum computers. Trapped ions and neutral atoms occupy a similar category. They offer excellent coherence and high-fidelity operations for computation, making them strong candidates for breaking classical cryptographic schemes once they scale sufficiently. But they are not designed to operate as communication layer security systems. Their environments, control methods, and operating constraints make them better suited to centralized quantum processors than to distributed security infrastructure. Topological approaches, if realized, could eventually offer fault-tolerant quantum computation with dramatically reduced error correction overhead, which would make them highly relevant for cryptanalysis. But today they remain experimental and carry significant physics risk, placing them firmly in the long-term computation category rather than near-term security deployment. The key takeaway from this mapping is that quantum security is not about picking the most powerful quantum computer. It is about choosing the architecture that aligns with the security task at hand. Photonic systems dominate secure communications, while matter-based qubit systems are primarily aimed at computation, including the eventual breaking of classical cryptography, and confusing these roles leads to unrealistic expectations about both timelines and threats. Here, we highlight a subtle but critical distinction in quantum security. Noise is not inherently good or bad. It depends entirely on who you are and what you're trying to do. On the left is the defender's view. When a quantum communication system operates with a low, stable, and well-characterized noise baseline, any external disturbance stands out clearly. An eavesdropping attempt introduces additional errors, excess loss, or unexpected fluctuations that rise above the normal background, making malicious interference detectable through metrics like quantum bit error rate or unexpected variance in measurement statistics. In this regime, noise actually helps the defender because stability turns anomalies into signals. On the right is the attacker's view. When the baseline noise floor is already high and fluctuating, small amounts of additional interference can blend in with normal system behavior. An eavesdropping spike that would be obvious in a clean channel can be hidden inside natural noise variation, making detection far more difficult. In this case, noise becomes a form of cover, allowing malicious activity to hide in plain sight. The key insight is that secure quantum systems do not benefit from being noisy. They benefit from being clean, stable, and measurable. Low noise improves key rates and system performance, but more importantly, it sharpens the defender's ability to detect tampering. High noise may appear to offer robustness, but in practice it increases uncertainty and expands the space in which attacks can remain hidden. This is why the quality and stability of the physical channel matter just as much as the cryptographic protocol layered on top of it. As we wrap up, there are a few key takeaways that cut across everything we've covered. First, quantum hardware choices matter far more than algorithms alone, because architecture determines noise behavior, scalability limits, and whether systems are even feasible outside the lab. Universality, while mathematically elegant, is not free in practice, since compilation depth and native gate sets dominate real performance. Error is not a single knob you turn down. It's multidimensional, with decoherence, control noise, crosstalk, leakage, and measurement error affecting each architecture in fundamentally different ways. Scalability turns out to be an infrastructure problem long before it becomes a qubit problem, as control, calibration, and operating environments tend to break systems before the quantum logic itself does. Quantum security and quantum computation are also not the same problem, which is why photonic systems dominate secure communication and key distribution, while matter-based qubits are primarily aimed at computation and eventually cryptanalysis. And finally, low, stable noise helps defenders, not attackers, because clean systems make interference visible, while noisy systems allow malicious activity to hide. The deeper lesson here is that security is not a static property you achieve once and forget about. It's an ongoing process of understanding tradeoffs, monitoring reality, and adapting systems as both technology and threats evolve. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.